So let's get started from the topic. We're going to look at different type of loading. In the last 3 weeks, in the last 3 weeks, we've been looking at a particular type of loading on a beam. So one is what is called transverse loading, where if that is the beam, where the loading is applied on the surface. And the one we did last week is a case where we have an axial compression where the load is applied along the length like that. Now we're going to move on to a different kind of loading where we are trying to twist the structure. So we are applying twisting onto the structure. So what we want to show is what is the link between the magnitude of the twisting moment you apply and the stress that you actually generate in that particular structure. And that will allow us to determine the maximum load you can put on the structure that you are looking at. So we will cover what is called the twisting moment. So that is the torsional moment, which I will show very, very shortly. And then we'll try and relate it to the stresses, which is mainly the shear stress. And then we'll use that to define what is the torsional stiffness, and also to relate it to the magnitude of the power you are able to transmit in a shaft. And we've already discussed bending moment. So I think for the last 3 weeks. So what we want to show now is the difference between bending moment and what is called twisting moment. So I cannot remember whether I went through that when we discussed bending moment. So I'll put here a simple solid circular bar. So let's assume that end is fixed. So if you look at the circular cross section, it has 3 main axes. One axis which is perpendicular to the surface, and the remaining 2 which are in the same plane as the surface you are looking at. So for bending moment, the moment is applied about to any of the axes that is in the same plane of that particular cross-section. And for a torque, the moment is applied on about an axis that is perpendicular to the main surface. So this is the one that we'll be looking at because it results in the twisting of that structure. We will soon see how we went through how we determine whether the bending moment is positive or is negative, and we went through that. We have similar type of convention for a twisting moment. So I'm going to do so. If my twisting moment is like that, so if you use your right hand thumb, I'm going to use that. If you use your right hand thumb to go through along the direction that you are twisting. So, and the thumb is pointing out from the structure, we will say we have a positive twisting moment. If I was twisting that way, and my thumb is pointing along the length of the bar, I've got a negative twisting. So in this case here, I would say I've got a positive torque. And because it's the same thing as moment, the units are the same as we have in bending moment, is Newton per meter. So I hope, I don't know whether you talked about twisting moment in your first year. So this is not a circular cross-section, but we'll be dealing with circular cross-section. We are trying to twist it that way. So, and we want to find out what is the link between the magnitude of the twisting and the stresses that you actually develop in that particular structure. So let's go to how we derive that relationship. So first, we'll go through some of the applications which I think some of you are already familiar with. So the most common one is where you are using it to transmit power. Anything that is transmitted power will have a particular value of torque associated with it. An example here is a drill bit. So you are basically transmitting power. There will be a torque applied. And many civil engineering structures, depending on how they are assembled, will also have some torque applied to it. And I met somebody who's doing petroleum engineering sometimes last week, Thursday. So that is not different from this. So if you have what is called a drill string with a drill bit at the bottom, so that is your drill bit, and you are drilling a well. In order to do that, you have to rotate this. You have to continue to rotate that so that drill bit will continue to drill. Therefore, it's exactly the same. It's exactly the same as that. So there will be a torque that you are applying to that particular drill string. So what we'll be showing now is what is the link between the magnitude of the torque, whether it's in the drill bit or in that simple bit there, and also in that particular case, and the magnitude of the shear stress that you develop. So let's look at a simple case. So I'm going to looking at circular cross-section. Let's assume that is my circular cross-section with a particular length. This end here is fixed. We're applying a torque T onto it. That shaft is got particular wall thickness, which is in green. So because of the magnitude of the torque that we are applying to it, if I had a straight line on the surface before this torque is applied, after this torque is applied, that straight line will have moved there. So this is after, and the one here is before. So if you draw a straight line onto the surface before you apply the torque, and after the torque is applied, that straight line will have moved there. And what we want to be able to show is that this magnitude of angle, which I'm going to call gamma, will have a relationship to the magnitude of the torque that you apply to it. But what will happen to that cross section is, if I look at just one small section there, if I blow that up, so what we will see is that that section there will have a shear force. Will have a shear force acting through the wall like that. So because of the magnitude of the twist that you are putting on it. So that will lead us to a shear stress, which is the magnitude of the shear force that is happening on the surface divided by the small area of that. I will say, as the area gets very small, we'll be able to get to the point there. So that cross-section will be subjected to shear stress. So, and it's the magnitude of that shear stress we want to find in terms of the size of that bar, and also the magnitude of the torque. So if we're able to do that, we'll be able to find the maximum torque you can put on that shaft to make sure that that shaft does not fail. So let's go through that. The derivation is not that long. It's very short, and the assumptions are very similar to the one we did in terms of bending moment, and we should all be familiar with that now. That plane cross section before and remain plane after the load is applied. The radar remains straight. So what that means is that any line on that cross section remain straight. So they don't bend. So they just get rotated about the particular axis you are looking at. And we are looking at small deformation. This one here means you are looking at small deformation. So we have a circular cross-section like a shaft. We apply a twisting torque in Newton meters. We want to find out what is the shear stress that is developed in that particular cross-section. So let's quickly look at what that will look like. So I'm drawing, so you'll be seeing this drawn many times. So that is similar to what I've just drawn. So I've got an initial line along the axis, and I've got a torque applied. That line has moved to a different location, and we want to look at what is the relationship between the movement of that line and the magnitude of the torque that you have on it. So let's look at that small angle. So if I had that initial line there and I have a circumferential line, it's very clear that the angle there will be 90 degrees, because the angle between a circumferential line and a line along the longitudinal axis will be 90 degrees. If we now apply a torque to it, that line has moved to the one that is called dash, dash, dash. So therefore, the angle is no more 90. The angle is now less than 90. And it has decreased by that small amount gamma there. So let's look at gamma is the change original 90 degrees angles. between longitudinal and circumferential. So a line which is along the longitudinal axis and a line which is along the circumferential axis, which were initially at 90 degrees before you apply that twisting moment. Now, so they've changed by a small amount, which is denoted by that symbol there. That would be our shear strain. I have a rough idea. You discussed shear strain in your first year. Is that right or not? No? Yeah, you discussed shear strain. So did you go through what is the difference between what is called true strain and engineering shear strain?
We had that this year, a little bit.
Sorry? This year?
Yeah.
All right, okay. Okay, so if you're here, what we now have here is what is called an engineering shear strain. Engineering shear strain you will get if you have a given structure. It doesn't matter what load you're actually putting on it. If you have a given structure where you have two lines which were initially at 90 degrees from each other, and then you apply some load to it, and the load is such that the angle is no more 90 degrees, the angle has changed a little bit. So that means you have a shear strain. So the magnitude of the shear strain is the change in that angle of 90. So if it was 90 degrees before, and it's now something like 89 degrees. So that 1 degree, so will be magnitude of your shear strain. So what we have here is our what is called the engineering shear strain. So I'll put here gamma is the engineering shear strain. You will see in the next slide, so we will try and explain how to find that in terms of the load. So here we have a solid rod, so initial radius of R0, and we've applied a torque T. The length of the rod is length L. It is fixed at one end, so to make it easier, but the other end doesn't have to be fixed because you can have it here and here. This is being twisted that way, and that is being twisted in the opposite direction. So you have something that goes like that. So I have picked a given point A at a distance R from the center, a given point A at a distance R from the center, and I've drawn a straight line along the bar before the load is applied, and the load is applied. That has rotated by a small angle gamma to a new point A prime, and that gives me a small shear strain there, so which I want to relate to the load. So that's what we want to show how we do that. So if you look at the mesh here, which is what I'm trying to show there. So this, if you had a bar like that with all the lines draw along the length and also along the circumferential direction, you can see they are all at 90 degrees from each other before the load is applied. Now the load is applied, so you've twisted the lines that are along the length. Now the angles are no more 90 degrees. So because of the shear strain that you've created in that bar. So we want to relate that shear strain to the load. We know if we have shear strain, we will have shear stress as well, and that is what we want to be able to find now. So let's see how we find that. And how we find that is very similar to what we've been discussing for beam in bending. So we're going to go through the basic derivation using this sketch here. So the same sketch, which we showed before. So I'll put here. So that twist there, let me just make clear, that is in radian. Every angle is in radian, and that is shear strain. That is dimensionless. Sorry?
Didn't you say that there was an angle as well?
Which one?
Down. The one on the right. Yeah.
Yeah.
So is it dimensionless or is it in degrees?
No, it will be, yeah. You will see when we show it, but that is shear strain, so strain has no dimension. So you will see very shortly why that's the case. Okay. So if we look at that bar at the top, the first one, so that's the one before the load is applied. The radius of the bar is denoted by uppercase R naught. So now I want to look at what happens when I apply a torque to it, but I don't want to look at what is happening on the surface. I'll pick a point at a distance R from the center, which is less than, my R is less than R naught. So somewhere within that particular large cross section. Well, we now apply our torque to it. So this torque in this case is applied like that. So that straight line has now moved a little bit. So the angle, which was 90 before, has now reduced by a small amount, which is called gamma there. So that's what we want to show. So to now answer your question, you will see here why it has no dimension. So if I look at B, A, and A prime, so what we will have will be something that looks like that. So if I make it slightly bigger, so I have L, I have here gamma, and I have here R phi. So if you look at that triangle, that's what we will have. So and if I now say what is tan gamma from that triangle? Sorry? R over L? Something is missing there. R phi over L, thank you. So R phi over L is that. So, but because we said we are dealing with very small deformation, so that angle gamma will be very small. And if the angle is very small, we'll say that tan gamma is approximately equal to gamma for small angle. So which means my gamma is R phi over L. So to answer your question, why is it dimensionless? So because if your R is in meters, your L is in meters, so that has no dimension, and phi is in radian. So now that we have that, so and I'm sure you also did in your first year, maybe this year, that if we have shear strain, so shear strain gamma is shear modulus. So it's shear stress divided by the shear modulus. So, sorry? If angle is not small, you can use this. Okay, so we are dealing with deformation that's very, very small, exactly the same as the beam. So everything we've discussed about the beam in the last 3 weeks, if you have large deformation in your beam, you cannot use them. Okay, so because that is something else you have to add to all the equations that we've done. So if the angle is large, then we will not be able to make that assumption. Okay.
What do you mean by R being smaller than R0?
Look, that bar is a solid bar with a radius of R naught. Okay. So we are looking at a point within the circular cross section. Okay, and that point could be anything between 0 and the surface. But I've said I'm picking an R that is length than the main surface of that bar. So if you look at that cross section, if I just draw it here like that. So that's your cross section. From here to there is our R naught. So the torque is applied, say like that. So we have a coordinate which is R, which starts from 0 to the surface. And what we want to find is what is the shear stress at the center? What is the shear stress when R equals, say, 1 millimeter, R equals 2 millimeter, whatever it is, until you get to that point. Because the shear stress is not the same at every point within that particular cross-section.
But it's technically the same structure.
Yeah.
All these images, they show the same structure in a
Well, it's not, the actual radius of that bar is that. Okay, this is the coordinate to tell you where you are within the cross section. Okay, yeah. So if we know the shear strength gamma, I can find the shear stress because the shear stress is just shear strength multiplied by the shear modulus. So the shear modulus depend on the material. So I think that's written right at the bottom here. I'm sure you've done that shear modulus related to the Young's modulus, according to 2 into 1 plus mu. So if we know Young's modulus and Poisson ratio, we can find the shear modulus of the material. So what this now tells us is that the shear stress that is developed in the bar depends on where you are, which is the Torsion coordinate R. So if we have R equals 0, we are at the center. If we have R equals R naught, we are at the surface. And anything that you have in between, we are somewhere within the large circular cross section that you are looking at. That phi there is what is called the angle of twist, is the relative change in the twist between the two ends of the bar, and that is measured in radians. So what we have here is good, but it does not allow us to relate it to the load. The load is the torque. And what we really want is to relate it to the load. So normally you want to find, if I apply this torque, what will be the stress? So at the moment, we cannot do that. We can relate the stress and the shear strain, but we cannot relate it to the load. What we want to show next is how we relate it to the load, which is the main one that we do need. So if we go to the next slide, we go back and use one of the main concepts which we've been trying to use many times, which I put right at the top again, which is that whatever stresses you develop within a structure, it must be in equilibrium with the load that you are applying to it. So if you apply a load, you develop some stresses, and that stresses must be in static equilibrium with the load that you are putting onto the structure. Let's see how we use that to relate the torque to the shear stress. So here I have a circular cross section, and my load is the applied torque. So I'll put here externally applied load is T. So that's that. And the stresses that are developed, the internally developed stresses, is my shear stress. So now what I want is to show that whatever stress that I have, it must be such that it is in equilibrium with the load that we are applying onto the structure. So it's a circular cross section. The outer radius is denoted by uppercase R, which is suffix naught. So now we apply a torque. We know we're going to develop some shear stresses. So I've chosen a particular small layer at a given distance R, and I'll look at what is the stress on that, and I'll take the moment and I'll equate it to the load that we are applying. So let's say the shear stress is acting like that, on that small layer, and like that. So that ring of material has got a shear stress tau that is acting on that particular surface. But what I want is the shear stress that is acting on the whole surface. So let's see how we apply the concept of the static equilibrium that we just said a few minutes ago. So if you look at that small layer, so the shear stress acting on it is denoted by tau. The area of that small ring would be what? If you look at that ring, it's inner radius of small r, thickness of the r. So if you are trying to find the surface area of that ring of material, what should that be? Pi over? Pi 2r. Correct. So do we all see that? So maybe the best way to do that is to use this. So if we have that, I want to find the area of that ring there. That's the area that we are trying to find. So if that inner radius here is our R, what is this circumference? Sorry? Pi to times the diameter. Okay, that's fine. So pi times the diameter. So that is similar. That's same thing as 2 pi r. Okay, right. So that's 2 pi r. But so if I open this up like that, what is this length? 2 pi r. Correct. So that's 2 pi r. So 2 pi r multiplied by the actual thickness of the paper will give me whatever area this is. So if we have a ring like that, so the area of that ring there, is the same thing as 2 pi r times whatever thickness that is. Because if you open it up, that becomes your 2 pi r, that is the thickness. So the area of that ring there will be 2 pi r times the r. So, but the shear stress is acting on that particular area. Therefore, that will give us a shear force, a small shear force of shear stress times the area, which is 2 pi r times the shear stress times the r. But the load we are applying is a torque. So that shear force on that element will have a small torsional moment acting in the opposite direction about the center. And that torsional moment will be, I will call it delta T, will be the shear force. Shear force times what? So we are trying to find what is the moment of that shear force on that ring of element, that the shear force will have a moment about the center. What is that small moment that is got around the center? What do we multiply with? So, R, that's right. So we multiply by R there. So, but we're only looking at just one small ring of element. But we have the whole of that particular cross-section. In order to repeat the same thing for the whole cross-section, we then have to take the whole integral from the center to the surface. So I'm going to apply this as 2 pi r squared to the r. Okay, so the total torque, therefore, so will now be the integral of delta t from 0 to r naught. So that is coming from that internal shear stress, but we now have to equate that to the load that is applied because of the concept of equilibrium. We will say that the torque that is applied must equal that integral of that times delta t. And that will give me this. So if we were to integrate that, what will we get? So we have tau, which we assume is constant, 2 pi r squared dr. So if we were to integrate that, and also noting that from the previous page, we've said that from 5.1 that the shear stress is equal to shear modulus times phi times r over L. So if we put that in, then we will end up with that equation 5.3. So now I want to do the actual integration of that. And once I've done that, that is the only thing I need. So the only derivation we need to show is the one that we've just shown here. So how do we integrate that? So what is the actual integral of what we have there? What's the integral of 2 pi r cube the r? Sorry? Half pi, okay. That's good. So I'm going to write that here. So on the next slide, so that integral is the one I call J, which I'm going to define now, is this second polar moment of areas, not the same as I. So let's look at what the actual integration is like. So I think somebody just told me that answer there. So we can say, therefore, J is 2 pi r4 over 4 between 0 and r naught. Yeah?
So can you go back to the previous slide? The previous one.
Okay. So if you look at that integral, so we have 2 over 4, which is basically half. So we can write this as pi of r naught 4 over 2. So our second polar moment of area, which is J, which you will see from now on, is given by that. If it is a solid cylinder, is that if it is a cylinder with an internal radius and also an outer radius, then it's basically the same. You just you use what is the value of the inner radius and what is the value of the main outer radius. Okay. Now I can use that and write my torque in terms of the twist and the torque in terms of the shear stress. So if we go back to 5.1 again and 5.6, we end up with this. So and that's the only thing. So now I want to start to use this. So let me just explain what that is. So here we have a circular cross section where a torque T has been applied, and that torque T would develop a shear stress tau at a given distance r from the center. R is measured from the center of whatever cross section that you've got. So maybe I'll make that clear if I draw the circular cross section here. So that can be hollow, it can be solid. I'll make it hollow here for now. So our coordinate r is from the center to the point where you want to calculate your shear stress. So this could be your inner radius, Ri. That could be denoted by outer radius, R naught. So T is the torque applied in Newton meters. Tau is the shear stress at a distance R from the center. Tau will be in Newton per meter squared. R is in meters. And G is the shear modulus of the material. And phi is the relative change in the actual twist between the ends of the bar. So if you are twisting it like this, what is the relative change in the twisting angle between this end and that end there? And L is the length, and J is the second polar moment of the area of that particular cross section. So J is in meter raised to power 4, R is in meters, L is in meters, G is in Newton per meter squared, and you will see as we start to use it. Okay, so that is the only derivation. So I'm going to start to use this. So, but I'm going to simplify it in a way that we can use it. So what we are saying, therefore, is that if you apply a torque, we will develop a shear stress. So let me just write the first one: shear stress based on the load, which is the torque, at a given distance r from the center, divided by J. J depends on the size of that particular circular cross section. And the angle of twist between the ends of the bar is the torque times the length, shear modulus G, and J. So what we have there, I've just used that particular equation. I've used the first two. I brought R from here to this side. So I now have shear stress equals torque times distance over J. That gives us the first one. And I've used the torque and this one to find the next one, because it's much easier that way. So now let's look at what that is telling us. So R is changing from the center. My coordinates, if I have that, R is changing from the center. That's like that. So if the radius of the circular cross-section is denoted by R naught, so it's very clear that for a given load, which is the torque, a given size, this is fixed. The only thing that is changing is that R will be 0 at the center, and it will be maximum at the outer surface. So the maximum stress you develop will occur at the surface of the shaft. So therefore, if we were to draw the shear stress, it will be increasing slowly from zero until you get to the outer surface. Right there is the torque times R naught over J. So because of that, if you are applying a twisting moment to a circular cross-section, and if it is going to fail at all, it's going to fail from the surface of the shaft, because that is where the stress has got a maximum value there. So that's where that is likely to fail. And because we are looking at small deformation, linear elastic, so the relationship between torque and angle of twist is usually linear, so it's linear like that. If you take off the load, and then it goes back to where it was before, so there'll be nothing, just like this. So if I twist like that, and I can see there, so it has deformed. If I take off the load, it just goes back there. So if you take off the load, it goes back to where it was before. So because there is no non-linear plastic deformation there. And the same thing with the shear stress and shear strain relationship will be linear as you apply your torque. And then, so if you take off the load, then it goes back to 0 there, mainly because it's based on linear elastic deformation. Because that is the one of the three main assumptions that we made there. So what we need, basically these two equations, or the main one which I showed previously, this one here. So there, because that's where that is from. So I'm going to end this section before I start to use them in terms of what is called torsional stiffness, so which comes from this. So here we have two things. One is the stress. One is the level of deformation. So the stress is tau. Level of deformation is measured by that angle phi. So we've already discussed designing for strength. Sometimes you design for stiffness. Okay, so they are two completely different things. So if you are designing for strength, then you want to make sure that this shear stress here is below a given value within the whatever material that you are dealing with, and that is based on the type of material. If you are using steel, for example, steel will have a maximum shear stress it can sustain before it breaks. If it is a simple concrete material, it will have a maximum shear stress it can sustain before it breaks. And therefore, you can then choose the load you can apply to make sure that that shear stress does not get to that value. That is designing for strength. But sometimes we want to design for stiffness, which means we want to minimize this value of deformation. So here, we don't want this to be quite large. So in order to do that, we introduce what is called torsional stiffness, which is the torque per unit twist. So this one here will be Newton meters per radian. So and that comes from that equation at the top there. We've already discussed stiffness before. So if you want to minimize the level of deformation, so what that means is that high torsional stiffness means low twist angle. And low torsional stiffness means high twist angle. So what tends to happen in many cases, if you ask many students or even young graduates and say, oh, so how do you reduce the stiffness of your structure? They will just say, oh, let's use a different material. But it's possible to reduce the stiffness without changing the actual material. So you can say the torsional stiffness there depends on the shear modulus. That is the only one that depends on the material, depends on the length, and depends on J. J depends on the size. So if the radius is very large, then J is also very large as well. So if I want to reduce my the level of deformation, I need to increase the value of the stiffness. And you can tell me here what I need to do to L. So if my aim is to reduce the level of deformation without changing the material, so what do I do to the length? Decrease it. So one option is to decrease the length, or to make the structure bigger, to make the actual radius bigger. If the radius is bigger, then J will go up, and therefore you can do that. So, okay, so let me move on to how to start to use it. So before, sorry, which one?
Yeah. So high S, could you put it down a little bit?
Oh, that, okay.
So the high ST means that
You have very high torsional stiffness, so that means that structure is very difficult to twist. Okay, so you need a very high torque to get 1 radian change.
also it doesn't determine the maximum angle before it breaks.
No, it's not like that. Okay, so here, the torsional stiffness is just telling you how easy it is to twist whatever you've got. All right, okay, so I'm going to round up now, and then we do few cases. So I've already explained torsional stiffness, so there's no, maybe I should write that here. So to reduce torsional deformation, so we have 3 options. So you can either increase G. That will mean you have to change the whatever material that you are using. Sometimes it's not possible to change the whatever material you are using because that is what is required for your design. Or we can increase J. That means you increase the radius. Okay? And the last one is to reduce L. Okay. So those are the three ways of doing that. Right, so I said at the beginning that if you have anything that you are using to transmit power, then you must have some torque there. So let's look at what is the link between the magnitude of the power you are transmitting and the torque that you are inducing in whatever you are using for that. So I'm going to start there. So we know, I showed before, if you have a car, you've seen the front of the car with your car engine. The actual power coming from the engine is fixed, so that doesn't change, and that goes into the drive shaft, and you use your gear to actually control the magnitude of the speed. By changing the gear, you are changing the magnitude of the torque. So what we want to show now is the link between the torque and the power there. So we know that power is measured in joules per second, which is Newton meters per second. Okay. So, and we know that torque is measured in joules or just Newton meters. So what that means is that there's a link between the two, because so what is the torque per second? So there. So if you look at that, so the frequency, which I think you are all familiar with, is number of circles per second, or you can say number of revolutions per second. Okay. So now I want to link all of that together. So if I'm transmitting power, I have a shaft that is rotating. So it is rotating, and I ask myself, what is the power transmitted for every 1 revolution, for every 1 revolution that we've got. So let's do that. So I have power per n rotations, or n revolutions. So what we have there, therefore, so that would be the torque times 2 pi, which is one revolution, times number of revolution per second. So if that's the case, what I have there, 2 pi n per second is my angular speed. So we can therefore write and say that power, which is in Newton meters per second, is equal to torque times angular speed. So torque times angular speed. My angular speed is in radians per second, so that we are very, very clear. That is in radian per second, and that is in Newton meter. So if I know the torque, and I know the number of revolutions per minute, I can convert that to radians per second, and therefore I'll be able to find the actual power that we have in that particular shaft. So if you look at the car, the example of the car, that does not change. That is the power coming from the main engine of the car. So when you change the gear, what you are changing, therefore, you are changing that speed through your gear change. And by changing that speed, you therefore have a different torque. So at low gear, when your speed is very low, then that torque is very high because this doesn't change. And at high gear, when your speed is very high, the torque is quite low. Okay, so that's it. I've got 5 minutes left. So I'm going to stop here. So I'm just going to write the main equation, and we will use that tomorrow. Hopefully, we'll finish this tomorrow. Let me just summarize this. All we've said is that for a circular cross-section, this is the main equation which we have derived. And that is what we need. That is the torque you apply. That is the shear stress you develop at a given distance r from the center. That is the angle of twist between the 3 ends, and that is the length of that particular shaft. And we will use that from tomorrow. Okay.